All right, welcome back. I hope everybody had a chance to look at the video that I posted yesterday. We're just going to continue on with these next two examples and hopefully finish up chapter 7 in this video. So let's take a look at C. Some of you guys recognize immediately that you can use the shortcut for this. And if you wanted to use a shortcut, if you remembered what it was, you could certainly use that. But what I'll do here is I'll just show you the box method again, so that way you can use it if you don't remember that shortcut. So again, let's create this box, 2 by 2. And remember, you cannot apply the rule where you can sort of distribute this square into both of these because this is a binomial. That monomial rule does not apply here. So this is going to be the square root of 13 minus 2, the square root of 13 minus 2, and then you multiply these out. You just get 13, because the square root of 13 times the square root of 13. These guys are going to cancel each other out. This is going to be negative 2 radical 13. This will be another negative 2 radical 13. These will not cancel out because they're the same value, so they're just going to combine, where in part B, the middle section sort of like cancel each other out because it was a difference in squares, but this is not. And this is positive 4. So our final answer here should be 13 minus 4 square roots of 13 plus 4. And then, of course, we can combine our like terms here. So that's going to give us 17 minus 4 square root of 13. And that's it for that one. This one's a little bit interesting because, again, you're not dealing with the square root here. You're dealing with the cube root. So we'll see how that plays out with the, is this a difference of two squares and how that's going to behave, okay? So let's take a look at this one using the box method again. All right. So let's do this. So this is 4. And then the cube root this time of 7. And this is 4 minus the cube root of 7. So that's going to give us 16. This is going to be 4 cube root of 7. This will be negative 4 cube roots of 7. So these will definitely cancel each other out because this is positive and that's negative. But this time when you go ahead and multiply these together, this is negative, and it's not going to cancel out the square root because you're only multiplying 2 of them. In order for this to go away, you'd have to have 3 of these. So this is going to be the cube root of 49. Not the square root of 49, the cube root of 49. So your final answer is going to be 16 minus the cube root of 49. So just be careful when you're messing around with the square root versus the cube root. In order to get things to go away effectively, you need to make sure that you're actually doing what you're supposed to do. In this case, it's the cube. Okay. All right, so now we're into rationalizing the denominator. So a common way of standardizing the form of a radical expression is to have the denominator contain no radicals. So remember, we had talked about the conditions of a simplified radical earlier, and I said at some point we're going to talk about that, and this is when it's going to happen. We cannot have any square roots or any radicals, for that matter, in the denominator. So we need to do what's called rationalizing the denominator. We do that by multiplying by some form of 1, whatever that form is going to take. Because remember, this is a 1. We know that for sure. This is also a 1. We know that definitely. This is also a 1. This is also a 1. And this is also a 1. I know it's crazy to think about it, but this is a value right here, and this is the exact same value, so this is a 1. So this is the idea that we're going to be using to try and rationalize these denominators, is we're going to multiply by some form of 1 to be able to get rid of the square root that's in the denominator, or the cube root, whatever radical we have down. All right, so I told you that this would come back, and here it is. So we have this 5 over the square root of 11. So again, it says we do this by multiplying by some form of 1. And that 1 that we're going to be looking for is going to be this radical 11 over radical 11. So whatever's down here, this is what's the problem for us. So this is what we're going to use to get rid of the radical in the denominator. So this is going to be 5 radical 11, because 5 times the square root of 11 is 5 times the square root of 11. And then the square root of 11 times the square root of 11 is just 11. And you can see now that we no longer have any square roots in the denominator. So we've done everything that we're supposed to do as far as rationalizing the denominator. Same sort of thing is going to happen here. This time we're going to multiply by radical 5 over radical 5, this form of 1 that we're searching for. And this will give us 5 radical 30 over 5. And then you can see that these 5s will cancel, and you're left with this square root of 30. And then you do have to check to see if there are any perfect square factors of 30. There are not. So this is our final answer here for example 3. All right, so let's take a look at this one. This one's a little bit more involved. What I would do first is, you could certainly, if you wanted to, multiply by radical 18 over radical 18. There's nothing that stops you from doing that. So if that's the first thing that jumps off the top of your head, that's what you're supposed to do, then go ahead and do it. But what I'm going to do is I'm going to look at this radical 18, and I'm going to recognize that there's a perfect square factor of 18 that I can take out. So that's going to end up being this -8 over, and when I simplify this radical, I get 3 radical 2, because this breaks up into the square root of 9 times the square root of 2, and the square root of 9 is 3. And now at this point, instead of multiplying by radical 18 over radical 18, all I have to do is fix this radical 2 that's down here. So I'm going to multiply by radical 2 over radical 2. This is the form of 1 that I'm going to use to get rid of this radical in the denominator. So that's going to give me -8 square root of 2 in the numerator, and this is going to be 3 times 2 in the denominator. And there's a reason why I left it as 3 times 2. Number 1 is to show you that this times this is going to be 2, but also so I can simplify that -8 and that 2, so that I'll get -4 square roots of 2 over 3, and that is your final answer for part C here. Again, you would get the exact same answer if you did radical 18 over radical 18. You would just have to simplify at some point. So if you want, I can just show you real quick what that would look like. So -8 over square root of 18. So I'm going to multiply by radical 18 over radical 18, and that's going to give us -8 square roots of 18 over 18. And now at this phase, you need to, again, simplify that radical. So we'll do that. So this is going to be, again, you can kind of simplify this first if you wanted to. Say, all right, this has a common factor of 2. So there's your -4 square roots of 18, and this is going to be 9. And now you need to get into this realm of the radical 18. So you've got -4 times 3 square roots of 2, because we know that this radical 18 simplifies to be 3 radical 2. We did that already, over 9. And now you can simplify here to get a 3. And our final answer is exactly the same as what we had over here. So again, it doesn't matter how you start this problem. I always find that it's probably easiest to simplify the radical first if you can, so that way you don't forget to do it later on, because a lot of students will think that their final answer is either this guy over here or this one over here, when in fact you need to take it out even further. Okay? Alrighty, so let's take a look at this one now. So again, this negative is on the outside here, so that's not going to bother us as far as taking the square root. So let's divide and conquer here. So this is going to be the square root of 8 and the square root of 45. So at this point, we can simplify this radical so that it's 2 radical 2, and this is 3 radical 5. So I've done what I needed to do as far as simplifying the radical 8 and the radical 45. Again, if you still haven't caught on, it's the square root of 4 times the square root of 2, and then the square root of 4 is 2. Over here is the square root of 9 times the square root of 5, and the square root of 9 is 3. So that's how I've simplified this radical. And then, of course, we need to get rid of this square root of 5 down here. That's a big problem for us because we can't, it's violating that condition of a simplified radical that says you cannot have any radicals in the denominator. So we're going to multiply by the form of 1 that we need, and that's going to give us 2 radical 10, and that's going to give us 3 times 5, which is just 15. And that's all she wrote there. All right, so again, example 4, A is in the books. And remember, radical 5 times radical 5 is radical 25. Square root of 25 is 5. 5 times 3 is 15. Or you can just see that these will cancel each other out instead of going through the motions there, and just say, well, this is just going to be 5 times 3, which is 15. All right. Okie dokie. So let's do this. And again, they need to tell you that y is greater than 0. You know, and technically k should be, you know, greater than 0 as well. So that way we don't have to worry about the absolute value and all that other stuff that comes along. So let's take the square root of 200, k to the 6. We're just dividing and conquering here, splitting up these radicals. All right, cool. And we're going to be able to do this one pretty quickly because, again, this is even. This is a 2. So this should be 10k to the 3rd radical 2. Again, because the square root of 200 breaks up to be the square root of 100 and the square root of 2, and the square root of 100 is 10. And remember the rule that says take this 6 divided by 2, you get 3. So your numerator was done pretty quickly. This one, again, is going to use that strategy that we used last week, where we say, all right, 7 is divisible by 2 3 whole times. So 2 goes into 7 3 whole times with a remainder of 1. So that's how this one simplifies. And then we just have to fix this radical y in the denominator. So we are going to multiply by the form of 1 that will do the job for us, which will give us 10k to the 3rd square root of 2y. And then what's neat about this denominator is that when you have the square root of y times the square root of y, you get y, right? Because that's the square root of y squared, which is just y. Well, you already have 3 y's down here. So now this is going to be y to the 4th, because remember, this turns into just a y, and then you have y to the 3rd times y to the 1st. When you're multiplying like bases, you add the exponents. There's those pesky exponent rules coming back again. Just when we thought we were safe from those exponent rules, they come right back. All right, so I think we're good. Maybe we'll do one of these just so we can make sure that we're safe here. This is a cube root problem, so it makes it a little bit more interesting. So we have the cube root of 15 and the cube root of 32. So again, this time we're looking for the perfect cube factors, not the perfect square factors. Remember, this is, again, going to be a little bit different for us. So this will break up, for sure, to be the cube root of 8 times the cube root of 4, right? Because 8 times 4 is 32. So this should be 2, because the cube root of 8 is 2, and then the cube root of 4. And nothing has happened in the numerator yet. So nothing has happened up there. Now, if you multiply this by the form of 1 that you think you need to multiply, it is not going to work. If you multiply this by the cube root of 4, it will not cancel this out. You need to be able to find the value that's going to turn this into a perfect cube, not a perfect square. So what I need to do here is the one that I'm looking for is the cube root of 16. The cube root of 16, because the cube root of 4 times the cube root of 16 is the cube root of 64, which is 4. Okay, so this should be, and I'll show you the breakdown here. This is going to be the cube root. I'll figure out what that is in a second. 2, and then this will be the cube root of 64, which is 2 times 4, which will give us 8 in the denominator there. All right, so please, 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 when you have this cube root, remember you're looking for perfect cubes, not perfect squares. So it's not enough to multiply by the cube root of 4 because it's not going to cancel. All right, it will not get rid of the radical. It's not enough to get rid of the cube root. All right, so just make sure that you're mindful of that whenever you're doing a problem that has the cube root involved. And then 15 times 16 is going to be 240. So 240, cube root of 240, and cube root of 240. So we should look to see if there are any perfect cube factors of 240, and it looks like there are. We have this 8. So we have 8 times 30, yep. So we've got the cube root of 8 times the cube root of 30 over 2 times 4. And the reason why I'm running like that, because this is going to cancel. So this is 2 cube roots of 30. And then 2 times 4. Again, these will cancel. And you're finally at our answer, which is cube root of 30 over 4. So these cube root problems are pretty tedious. So just be careful with those. Make sure that you're doing them correctly. Otherwise, you might get bit. Okay. All right. So this is where things get a little bit interesting. Is rationalize the denominators when you have a binomial in the denominator, because multiplying by just a single radical is not going to do the job for you. And here's why. So if you say, all right, well, I have a square root of 2 in the denominator, and that's what I'm trying to get rid of. If you multiply this to try and rationalize it by the square root of 2 over the square root of 2, remember what's going on here. These are in parentheses. So this is going to get distributed into both of these. So all that happens is that your radical 2 just gets put into a different spot. So this is going to be 3 radical 2 over the square root of 2 plus 2. And now what are you going to do? You got to multiply by the square root of 2 over the square root of 2 again, and that's just going to put it back over here. So it will not do what you want it to do. So don't bother. You're going to use what's called the conjugate. And the conjugate is creating this difference of 2 squares business that's going on here. So these are the conjugates. Same stuff. 1 and radical 2, 1 and radical 2, 1's plus, 1's minus. That will get rid of the square root that's in the denominator, or whatever radical is in the denominator. All right, so let's take a look at this. Again, I have a binomial in the denominator, so I need the conjugate first. So the conjugate of 2 minus the square root of 3 is going to be 2 plus the square root of 3. And that's the one that I'm going to be multiplying by. So 2 plus the square root of 3, 2 plus the square root of 3. And I'm going to do the numerator first, just because that's just going to distribute the 4. And I'll probably put these in here just so you can see it. So this is 8 plus 4 radical 3. And remember, I told you guys to get friendly with that, that shortcut when it comes to conjugates. It will make your life a lot easier. So this squared, the first part squared is 4. The second part squared is 3. And you just subtract them. Remember, the idea here is the shortcut is x squared minus y squared. If it's a difference of two squareds, that's how you're going to get your result in the path of least resistance. So 4 minus 3 is, of course, 1. So our final answer is just 8 plus 4 radical 3. So yeah, definitely get to know that shortcut when it comes to multiplying by the conjugate. The denominator becomes like the easiest part of these problems if you know the shortcut. So square the first, square the second, subtract, and you will have the number that's in the denominator. Remember, you shouldn't have any radicals left down there. All right, so again, I need my conjugate. So my conjugate of this denominator is going to be the square root of 2 minus the square root of 13, because it's the same stuff, 1's plus, 1's minus. So that's what I'm going to be multiplying by to the numerator and the denominator. Cool. And of course, the denominator is, again, the fastest part of this. When you square the first, you get 2. When you square the second, you get 13. When you subtract them, you get negative 11. So that, again, should be the fastest part about this problem. And then you have to just distribute that, and you get 7 radical 2 minus 7 radical 13. And this should be over the whole thing, or under the whole thing. All right. Very good. Very good. So let's do this one. And I think this will probably be it for this section. All right. So sorry, let's go back here. So again, our conjugate is going to be radical 2 plus radical 7. So that's what I'm going to multiply by. So radical 2 plus radical 7, radical 2 plus radical 7. So again, the denominator should be the fastest part of this whole process. Square the first, 2, square the second, 7, subtract them, you get negative 5. The numerator here is pretty tedious. So what I'm going to do is I'm going to use the box method to make sure that I get all my ducks in a row, to make sure I have everything that I need and I don't forget anything. So the square root of 3, the square root of 5, square root of 2, and square root of 7. So this is square root of 6, this is square root of 10, this is square root of 21, this is square root of 35. And the next thing I'm going to do is see if I can combine any of this, and the answer is no, because remember, in order to add and subtract radicals, you have to have the same index, which we have, but you have to also have the same exact radicand, which we do not have. But we should check to see if there are any perfect square factors, and there are not. So this is our numerator. So our numerator is going to be square root of 6 plus the square root of 10 plus the square root of 21 plus the square root of 35. And that is all she wrote. Okie dokie. So just make sure that you are getting the conjugate correctly, and then make sure that you are just being careful about finding the result of, especially when you're multiplying two binomial radicals together. This can sometimes be a little tedious to make sure that you have everything that you need. All right. So let's take a look at this. So radical equations using the power rule. So this would be pretty sweet for us. We're going to get into equations. It seems to always be like the last section that we do in these chapters, is to solve equations with whatever it is that we just learned. All right, so the power rule says, if both sides of an equation are raised to the same power, all solutions of the original equation are also solutions to the new equation. So squaring both sides or cubing both sides will not change the solutions to the original equation. So if you have radicals in your equation, especially if you have a variable that's trapped under that radical, your job should be to untrap it by either squaring or cubing or raising it to the power of 4, whatever index you have, that's what you're going to have to do to both sides of the equation. All right, so the power rule does not say that all solutions of the new equations are solutions to the original. So what ends up happening here is you end up getting sometimes these false solutions, because when you square something, you end up, getting rid of the radical, and we know that we can't take the square root of a negative. So, if you are getting a negative answer that's underneath that radical, we're forcing it to happen when it really shouldn't. And the only reason why it's happening is because we squared both sides to get rid of the radical. So this process oftentimes leads to these false solutions. So you should definitely check the solutions to make sure that they work. So such solutions that do not satisfy the original equation are called extraneous solutions and must be rejected. So usually we just kind of like cross them out and say, no, you are a false solution. You're not actually part of my solution set. All right, so let's take a look at this. So again, we have this radical of 5x plus 1 equals 4. When you're using the power rule, you want to make sure that you isolate the radical, meaning you shouldn't be adding or subtracting anything to that radical. You need to move it to the other side of the equation before you square. Otherwise, you're going to be having to do binomial multiplication with that radical, and it will not be very fun. So just make sure that you isolate this radical, which this already is. So there's nothing being added or subtracted on either side of this radical. So let's go ahead and square both sides. So we're going to square this, and we are going to square that. So again, that will do a great job for us because it gets rid of the square root. These cancel each other out and leaves us with just 5x plus 1 equals 16. And this is about as garden variety an equation as we're going to get. This brings us right back to chapter 1. So we subtract 1, 5x equals 15, x is equal to 3. So this is our proposed solution. We should check it to make sure that it is valid. So we just throw this 3 back into the original equation. So 5 times 3 plus 1 equals 4. So this is going to be the square root of 16 equals 4. And the square root of 16 is definitely 4. So this checks out fine. So this proposed solution is a valid solution. It is good to go. We didn't get a second one. That was an extraneous one. So we don't have to worry about that. All right, so this is talking about isolating the radical, applying the power rule, solving the resulting equation, and then again, check all proposed solutions to make sure that everything checks out correctly. All right, so let's take a look at this. So we've got this square root of 5x plus 3 plus 2 is equal to 0. So this is what I was talking about, where you need to make sure that you're not adding or subtracting anything to your radical. If you are, you need to move it to the other side of the equation. So when we do that, we get minus 2, which gives us the square root of 5x plus 3, extend that, is equal to negative 2. And what's nice about this is that we can stop. Because if you take the square root of a value, doesn't matter what's in here, you're never going to get a negative here. The square root of 9 is 3. The square root of 16 is 4. The square root of 100 is 10. The square root of negative 100 is not negative 10. The square root of negative 4 is not negative 2. So this right here is a no solution situation. But let's suppose you didn't see that, right? Let's suppose you didn't recognize that this shouldn't be a negative over here. And you said, all right, I've done what I need to do in order to apply the power rule. So let's apply the power rule. Let's apply the power rule to see what happens. So we get 5x plus 3 is equal to 4. And then we subtract 3, and you end up with 5x is equal to 1. And then you divide by 5, you get x is equal to 1/5. So you get a solution if you apply the power rule. The problem with this solution is that it is junk. So, and I'll show you what I mean by that. If you plug it back into the original equation, the square root of 5 parentheses 1/5 plus 3 plus 2 is equal to 0. Well, this is going to be the square root of 1 plus 3 is 4, plus 2 is equal to 0. 2 plus 2 equals 0. 4 is equal to 0 is definitely garbage. That is not a valid solution. So we should have stopped right here, but we got sucked into this problem by realizing that I can apply the power rule, but I really shouldn't have because this was a negative over here on the right-hand side. So we ended up getting this solution, but when we substituted it back in, we saw that it was actually not a valid solution. So since it was the only one that we got when we solved the equation and it wasn't valid, that means there is no solution to this equation. All right, so let's take a look at this one now. So again, this radical is isolated. The new problem that we're going to have is that this is a binomial. And remember, when you apply the power rule, so we're going to apply the power rule, we're going to apply the power rule, bam, bam. You cannot distribute this 2. You have to multiply that binomial out. That's a common error that I see from a lot of students is that they write this right-hand side as x squared plus 1, but it is not x squared plus 1. This right-hand side is x squared plus 2x plus 1. When they multiply these binomials, so if you wanted to do that using the FOIL method, right, you would get x squared plus 1x plus 1x plus 1, and 1x plus 1x is 2x's. So please make sure that you're being careful so that way you are multiplying the right-hand side of this equation correctly. And that's just going to give us 5 minus x on the left-hand side because these will cancel each other out very nicely. And now we just start to do some other things. So we have an x squared part to this, and this isn't going away anytime soon. And at this point in the course, the only way that we can solve quadratic equations, things that are, degree 2 equations, is to make sure that it's equal to 0. So it's not equal to 0 right now. So I'm going to move all this stuff to the other side of the equation by subtracting 5, adding x, and that gives us a 0 on the left-hand side. And that's equal to x squared plus 3x minus 4. And now this is a factorable quadratic. So that's going to give us 0 is equal to x plus 4, x minus 1. And now when we solve these, when we set these equal to 0 using the 0 factor property, you get 2 solutions. You get x equals -4 and x equals +1. You definitely 100% should be checking these solutions, especially when you get 2. Be very suspicious that one of them is probably not valid. So what I'm going to do is I'm going to substitute this -4 in to our original equation. So we have the square root of 5 minus -4 is equal to -4 plus 1. So that's going to be the square root of 9 is equal to -3, and that is not a valid solution because the square root of 9 is +3, not -3. So you are no good. So my guess is that this will probably be fine, and it is. So if you do 5 minus 1 equals 1 plus 1, you get the square root of 4, which is 2, and 1 plus 1 is definitely 2. So this is our valid solution, and the -4 is not. All right, so let's go ahead and do this one now. And I think that'll be it for us as far as this chapter is, because, oh no, we got one more to do, sorry. So let's apply the power rule, because again, this radical is isolated. So when we apply the power rule, we're going to get 1 minus 2x minus x squared, because the square root will just cancel out, is equal to x squared plus 2x plus 1. We literally just saw this one. So we're just going to, apply that power rule again. When you square it, that's what you get. And then again, we start to move everything to just one side of the equation. So that way we can see how this is going to play out. So we are going to subtract 1, add 2x, add x squared, and we're going to get 0 left on that side. And we are going to get 2x squared plus 4x and a 0. And since this is an equation and it's equal to 0, we can divide everything by 2. And that gives us 0 is equal to x squared plus 2x. And this is factorable, so we have an x in common. So we use that fundamental principle. So 0 is equal to x x plus 2. So now once again, we get two solutions. We get x is equal to 0, because again, we use the 0 factor property, and we get x is equal to -2. Check them. Check these solutions. My guess is that this one is junk, because when you substitute that -2 in here, you get -2 plus 1, which is -1, and you're never going to take the square root and get a negative answer here. So this is not good. This one probably is fine. I should check it, so let's just do that real quick. 1 minus 2 times 0 minus 0 squared is equal to 0 plus 1. So this is going to be the square root of 1 is equal to 1, and that is true. So this is, in fact, valid, so we are good to go there. All right, so let's do this last example, and we can be done with chapter 7. So just because there are no numbers here doesn't mean that we still can't do what we should do. If we are trying to solve this for r, one of the problems is that r is trapped. R is trapped here in this radical. So if we want to untrap it, all we have to do is square both sides, and that gives us z squared is equal to r over t. And now we can solve for r by multiplying both sides by t. So that gives us z squared times t is equal to r, and then that's it. All right, so again, if your variable is trapped under that radical, that square root, make that square root go away by squaring both sides. If it's under a cube root, then cube both sides. Just make sure that you are applying the power rule correctly to undo whatever index of this radical that you have. All right, so I hope that you found this video helpful. Enjoy the rest of your day, and I will see you all on Friday for our Q&A session, and then I will activate our next test, which will cover chapters 6 and chapters 7. So again, have a good day. Thank you very much for listening.